This chapter, this is covering the periodic table trends that I'm doing for people. It's such a short chapter, I figure I can go ahead and do that very quickly. So, when we talk about periodic table trends, the way the periodic table was organized, it was organized in a way that there are some things that we can know about atoms based on where they are arranged in the periodic table. Now, the question comes down to is, all right, what's a trend? Well, if we look at a trend, we can talk about a trend in cars. The 67 Mustang and compared to the 2014 Mustang, definitely there are some changes that happen, much more sleek, aerodynamic styling and all that. But a trend is a predictable change in a certain direction. And the periodic table is no different from that. So for us, when we look at the periodic table, there is the atomic radius. How wide is the how wide is the atom from the nucleus to the outer regions? Thinking about those electron orbitals, those electron clouds, the energy levels that we had in the last chapter. And one of the things that we notice is as you're going from the right to the left, it's going up. As you're going from the top to the down, it's also going up. So if we're going down a group or a column on the table, the element's atomic radius actually gets larger. Well, why is this? Well, here's the thing. When you go down each row like this, okay, let's see if I can go ahead and call up the periodic chart for a moment. When we're going down each row, that means there's another layer of electrons that are added. And what happens is that actually makes the atom a little bit wider, a little bit bigger as we're going down this way. Okay, now on the other side of the coin, as you move across the period, if we're going from left to right, then it actually shrinks a little bit. The radius actually decreases a little bit as we're going from this way, going this way. You'd say, but well, wait a minute, what's going on? Well, remember, as you're going across, remember your atomic numbers, that as you're going up, you have more protons in the nucleus. More protons in the nucleus means more of a positive charge. And remember what Paul Abdul told us, opposites attract. So what happens is that the nucleus is putting a little bit more attractive force on the electrons and it's trying to hang on to it a little bit more tightly. That was the idea. Okay? All right. As we move on, okay, in Romans 12:2, but be transformed by the renewing of your mind. When somebody becomes a believer, there's a change that goes on in the mind. It is a lifelong process, okay, and it's spent with God. While we do have trends and the changes that happen on the periodic table, same thing for the new believer as well. It is a lifelong journey, something for you guys to think about. Now, here's the other thing. Another example of a trend is if atoms pick up or lose electrons, they actually get larger or they get smaller. Ooh, that's kind of a no-brainer here. So let's go ahead and let's take a look at a couple of examples here. We can go ahead and look at our friend sodium, and we can look at our friend over here, chlorine. Now you kind of notice that you have two circles there, and one is definitely a lot larger than the other. Well, if we take a look at sodium, remember sodium has an atomic number of 11, which means it's got 10 electrons to begin with, 1s2, 2s2, okay, 2p6, remember those electron orbital notations? And then, of course, there's 3s1. Well, okay, there is no 1 there. We can cross that out. I told you this video would be raw and unedited. Okay, so we got 1s2, 2s2, 2p6, and 3s, which, remember, what is the highest energy level? It tells us how many valence electrons it has. This has 1 in its valence electron, and what's the magic number that you need? Well, that's the ocho, isn't it? It's a big whopping 8. It blows away, so this is sodium right here. Okay, this is sodium with its 11 electrons, meaning 1 in that outermost layer. The moment it gets rid of it, look at the size now, it's sodium plus. Okay, it lost a lot of its size. Well, wait a minute, how can getting rid of 1 electron drop the size? Well, remember, if you get rid of that electron, you drop an energy level, don't you? you lose a chunk of that Ontario Mills. Think about it that way. Now we go over to chlorine. Chlorine is the opposite. Chlorine, on the other hand, we can talk about 1s2, 2s2, 2p6. Oh, wow. Then we have 3s1, 3s2. Okay, there's 3s2. Okay, and then we have 3p1, 3p2, 3p3, 3p4, 3p5. Woo! 3p5. And notice what happens, ladies and gentlemen. We look at how many valence electrons would chlorine normally have? Well, if we look at our highest energy levels there, that's the secret. It's got 7 valence electrons, and that's where it is right here. That's our original size of the chlorine. However, guys, pick up an electron, guess what? It gets huge. Well, wait a minute. Why is it getting huge? Because it's not going to be 3p5 anymore. It's now going to be 3p6. So it gained that size because of picking up the electron. So the main idea as a trend, if an atom loses electrons, they become smaller. If an atom picks up electrons, they become bigger. Yeah, exactly. That's the basic idea. So this is another trend that we do see in the periodic table. Okay, and I included this chart so you guys can see the differences between the different elements when they are at that neutral state, in that neutral state like sodium here. But the moment it gets rid of the electron, it becomes a lot smaller, right? But it will have its full 8. And that's kind of the name of the game here. All right. I already showed you guys how to read the table, okay? And of course, why sodium is it larger in its natural state? Well, remember, it wants to give away that 1 electron on its valence outermost level. And that's the bottom line I say here. Give away electrons, atomic radius drops. Pick up electrons, atomic radius goes up. Lead poisoning in Rome, and how light bulbs work. There is the idea that with Roman emperors, there was this idea that a number of them, that they went crazy because they had lead plumbing in the palace, and they would get the water through the lead pipes. They would drink their wine and whatever other liquids they drank in lead goblets. And the idea is that when you accumulate lead in the human body, it slowly poisons you. And their crazy idea, well, maybe not so crazy, that maybe the lead poisoning drove them mad. I think that might be a source, but I don't think that's going to be the overall thing. However, here's a quick one for you. Nero, an emperor of Rome, he was really, really a bad person. And it got to a point where he took his horse, went into the Roman Senate, and basically told the senators, "You're making my horse a senator because if you don't, I'm going to kill all of you." Well, Rome had a senator. That was a horse. All right. I talked a little about carbon and alloy steels. Again, you can read up on that stuff. And I know I broke my own rule about not telling stories, but I had to, at least for the Roman one. But now we have to talk about ionization energy, electron affinity, and a melting point. Okay, these notes are going to be a little bit redone for you guys. I will give those out for the honors chemistry guys because I do cover some more detail. But here's the idea. The ionization energy is the energy you need to take an electron from an atom. So in other words, you are taking it and you are changing the positive negative side of it. So if we look at lithium plus energy, we'll end up getting lithium with a positive charge and an electron. That's what we mean by ionization energy. Some of those atoms, it's going to be very easy to go and pull the electron out, like sodium. Think sodium, even lithium, it's not as big of a deal. But man, when you go down to chlorine, oh my gosh, much harder. Well, wait a minute, how come? Well, remember, chlorine has 7 valence electrons in its natural state. It wants 8. It would much rather go pick up an electron than go and lose the electron. So what do we have here? This is the ionization energy. And when you go across the period, like this, what we are seeing, ladies and gentlemen, is the trend that it goes up. So if we look at hydrogen to helium, for example, hydrogen has 1 electron, helium has 2. Okay, well, hydrogen is tiny. You can pick it up. It's not the end of the world. But man, look at helium. Helium is more of an issue. Okay, helium has got 2 valence electrons. It's happy because the Ocho rule, while the idea applies to helium, it's small, so the most it can take is 2, and that's its full outer shell. And here's the kicker. You look at helium and neon and argon and krypton. Now remember, these guys have their full outer shells, right? And yet, how come helium, being smaller, it takes a lot more energy to rip those electrons out? That's because if you look at helium, it's closer to the nucleus. And when those electrons are closer to the nucleus, remember, what's the charge of the nucleus? Okay, if you don't know the answer to that one, what is the nucleus made up of? Made up of protons and neutrons. So what's going to happen is the nucleus is going to put a stronger pull on the electrons here for helium than it will for, say, krypton or argon or even neon. So it's going to actually be harder to go rip out electrons for helium. Now we go to the other side here and we look at, it doesn't take as much energy to pull an electron out of a hydrogen or a lithium or a sodium or a potassium. You kind of notice, well, remember these guys, they only have 1 valence electron. They're more likely to want to get rid of it, so you don't need that much convincing. You still have to put energy into pulling it, but my gosh, compared to this? Really? Yeah, so, and the big deal about that, guys, is that kind of explains to us the behavior of these atoms. Why is it some of the atoms, they react the way they do? That's kind of the big picture of the whole thing. So when we go down here, you kind of notice it takes less and less energy to pull it out. Well, why? Think about it for a moment. If you're going down this way, every time you go into another row, you have another layer of electrons added. So the more electrons you have, the easier it is going to be able to pull it out. Wow, that is something. That really is something. So you come down here between hydrogen and francium, or francium. Francium is going to be easier to pull out electrons from compared to the hydrogen. Same idea here. It's easier to pull out electrons from radon compared to helium. So as we're going down the group, down the column, that ionization energy actually decreases. Now, can we apply the ionization energy idea to other electrons in the same atom? Yes. And it does take more energy to pull out the second, and then the third, and then the fourth. It depends. Okay? Now, we talked about why it increases going across a period. You add more protons to the nucleus. Okay? That's the idea. It holds the electrons more tightly. You need more energy in order to remove it. That would explain why it's going up like this. And you'd say, but wait a minute, why is it going down? Well, remember, there's certain levels that are filled up. So when you go to the next level here, it's not as big of a deal to remove it, but look what happens in between oxygen and fluorine and neon. So when you get closer to filling your outermost level, like a noble gas like neon, it takes a lot more energy in order to pull that out. Now, we talked about the ionization energy decreasing as you're going down a group. We talked about that. Going down a group, there are more energy levels. They hold on the electrons not so tightly, they're easier to remove. Now, if you increase the distance between the electron and a proton, that means there's a decrease in the attractive force, and that's Coulomb's law. If you stop and think about that. Coulomb's law talks about that. Now, if you think about the CEO for a moment of a company, if you have a CEO of a company who has 5 employees, it's pretty good that the CEO is going to be able to keep an eye out on those 5 employees, what they're doing, you know, are they using the equipment right, all that other stuff. Now, what happens though if the CEO, now his company has grown and now it's 150 employees. Now this becomes much more difficult. This becomes a harder thing to do for the CEO. And it's just the same thing. When the atom gets larger in size, when there's more electrons, it's easier to actually take an electron away. Okay? Pop star fans with security from few to many fans out there. Okay. We talk a little bit about electron shielding, just a tiny bit. Here's the idea. You can cut down on the amount of attractive force between a positively charged nucleus and the outermost electrons due to the cancellation of some of the positive charge by the negative charge of the other electrons. Wait a minute, what do you mean? Stop and think about this for a moment. If you have your pop star, okay, and notice I'm not using names, so I don't have to deal with issues, okay, and here you got the big burly, you know, security guard. Okay, and then you got the fans, and I'm going to put X's to so our pop star is surrounded by her security people, okay, and you got the fans. Hey, I teach chemistry, I'm not an artist, so don't sit there and chuckle about my artwork. I'm trying to prove a point. Now we have all these fans and they all want the pop star to sign their autograph. They want her autograph, okay? And we're going to assume that the pop star in this case is a she. So the thing is that some of them, they'll be able to get that autograph, some, like the ones who are closer. Now they can't touch her because of the security guards that are there, the bodyguards. Now these are big, tough guys. But what happens when you get some of the fans that are on the outside, they want to get to, they want the autograph. They're attracted to the pop star, just like the electrons are attracted to that positive nucleus, but there's so many other electrons in the way. So many fans in the way for these fans to get the autograph, just like there's so many electrons in the way for the other electrons, that what happens is those electrons, they act like a shield. Just like all these fans here, they act like a shield, and it makes it harder for these fans to get autographs on the outside. And what happens is they eventually give up in real life. They get discouraged and they walk away. Most likely that would happen in real life. Okay? So, I wanted to point that out for you guys. Okay, I'm going to have to erase this. And my time is running short. I do have a time limit here. So, we talked a little bit about electron shielding and some of the trends that we have going on in the periodic trend. And you may notice, if you notice this, the periodic trend in ionization energy is the opposite for that of the atomic size. Whew, wow. Yeah, the periodic trend in ionization energy, okay, is opposite of that for the atomic size. So here's the atomic size right here. Here's the ionization energy. They're opposites of each other, which kind of explains a few things. Okay, this is it for Chapter 8, ladies and gentlemen. And I hope that this will benefit you. Like I said, you guys will get the complete notes for those that I'm aiming this for originally. And for those of you who weren't here for that, well, this is it. All right, take care.